Okay, so before we actually get into the proof of the equivalence of those definitions, it's going to be very useful to define this notion of an inner regular set. Now, actually, I could say that the inner regular set, right, being irregular, is actually equivalent to being measurable, right? So this could be yet another definition of measurable sets for us. For one reason or another, I'm not going to really regard this as a definition, but it will end up being equivalent to measurable sets where we, using either Axler's or Carathéodory's definition of a measurable set. So this is equivalent, but I'm not going to actually take it to be a definition for some technical reasons that I don't necessarily want to discuss right now. But so let's say what it is to be an irregular set. So a set E is called irregular if, in a sense, it can be approximated from below by closed sets. That is to say, right, so what do I mean by approximated? I mean that we're going to take some positive real number epsilon to be like an upper bound on the error of the approximation. I haven't said what the approximation is, but that's the role that epsilon is going to serve once I tell you how this approximation goes. So there's going to be an upper bound on the error of any given approximation, and it is going to be approximated by some closed subset, right? So F is going to be some subset of E that is closed, and the difference between E and F is going to be less than epsilon, so that in a sense, F is contained within E, so it's in that way kind of like it's in the same area as E is. And it's most of E, right? If you took E minus F, there wouldn't be much, right? You could make that approximation small. So this is almost like the Axler definition of a measurable set, except that rather than talking about Borel sets, which is a bigger class, right? We know the closed sets are contained within the Borel sets. So F being closed is kind of a stronger, more specific kind of set. And for that reason, right, in some way that's kind of why we can't just say that the measure is zero, because we really need the fullness of the Borel sets to get that. But if we do impose this stronger requirement that F is closed, we can still say something quite useful, which is namely that although the measure may not always be zero, or we may not always be able to find a closed set F such that the measure is zero, we can always find a closed F such that the measure is very small, right? The measure of the difference. So anyway, that's the idea of an irregular set, is that it is an approximation from below, right? I say from below because F is contained within E, and as the error gets small, you imagine that the closed sets F that you pick kind of expand out to get closer and closer to capturing all of E. So anyway, so again, this is approximation from below of a set by a closed set. And whenever something can always be approximated from below by a closed set, we call it an irregular set. Okay. And the broad strategy behind what we're going to do in these proofs of equivalences is basically, I'm going to show that the set of all irregular sets, which I'm calling this calligraphic M, is equivalent to the set of measurable sets according to Axler's definition. Then I'll show that this set is also equivalent to the set of measurable sets according to Carathéodory's definition. And then after that's done, we'll know that all of these are equivalent to each other. Okay, so that's the big plan, right? That's why I'm bringing up these irregular sets. Now, we are talking about set differences, and here with closed sets, but also when it comes to Axler's definition with Borel sets. And so we would really like to have a few helpful tools to be able to compute these measures of differences for the later tasks that we have, right? So it would be nice to just have a few theorems, lemmas, whatever you want to call them, that aid in computing these set differences. So to that end, I'm sort of concocting a term. I don't know if there's another word for this, but as far as I know, there is no word for this. So I'm just going to make up some vocabulary and call a subset of the real numbers relatively additive, by which what I intend to communicate with this term is that a set is relatively additive if it with any set has the additive property that we've cherished this whole time. So to make it more formal, a set is relatively additive if you could take any disjoint set, right? A may not, is any set. It has no special sort of restrictions on what A is. So if A is any set, so long as it's disjoint. Okay, well, one restriction, A must be disjoint from E. But whenever you have a disjoint set, the M star of the union decomposes like additivity says, right? So again, E is relatively additive if it has the additivity property with every other set, right? As stated, we don't know whether anything is relatively additive yet. But of course, that's going to be kind of one of our first important tasks, is to state and then prove a theorem about open sets, right? So I want to claim that open sets are all relatively additive. That's going to be my immediate task. It'll follow fairly quickly after that. Several other theorems will kind of come quickly, right? We'll get closed sets. We'll get, several other sorts of sets. But for now, I just want to state and prove this one. So that's in the next part. Okay, so to get started on the proof, we'll take an open subset of the real numbers. Just to get one case quickly out of the way, suppose that open set has outer measure infinity. It's very easy to handle because, of course, basically just turns everything into infinity, and then you have equality, right? So this one is infinity, and this one is also equal to infinity because, right, non-negative number plus infinity. So there you have equality. So the case where the outer measure is infinity is very easy. Okay, so next we will suppose that the measure of G is finite, and further we will assume, this special case where G is this open bounded interval, right? So in this special case, the proof strategy is going to be to consider an arbitrary open interval cover of this whole set, and then we'll show that the sum over its lengths is greater than or equal to this, right? Effectively, what we'll be doing is we'll be showing that this quantity is a lower bound over all the overestimates of this union, right? So this is a lower bound on the overestimates, and then by definition of M star here, as the greatest lower bound, it has to be greater than or equal to any other lower bound. So that's the kind of big picture map of what we're going to show. So we're going to take A union G and the open interval cover, the I sub n's that cover it, and we're going to decompose those I sub n's into two families, two subfamilies or something like that, kind of. we're going to get the portion of each I sub n that is, so to speak, responsible for covering the interval from A to B. The idea being that if you slice out just this portion of it, that this family Kn now becomes an open interval cover of the interval from A to B. Very easy to prove that's true. I leave the proof of that as an exercise, but that's the idea, is that these Kns, these slicing out of the interval In for just the part that covers, or when you put them all together, covers the interval from A to B, we're going to get that open interval cover and then be able to sort of say something about that. Then we'll also get everything else, right? And so A might be a little bit out here and a little bit out there. Who knows what A is like? We just know that it is disjoint from the interval from A to B. So it's living somewhere out here. And so it's going to get covered on the left side by the JNs, on the right side by the LNs. There's a similar logic that, you know, when you slice this out and put the JNs and the LNs together, you're going to get an open interval cover of A. That's almost true, except for the possibility that A might contain the points A and B, and then these cease to be covers, right? Because they necessarily lack the points A and B no matter which N is chosen. So what do we do about that fact? Well, what we're going to do is we're going to assume that A lacks the points A and B, complete the proof, and then once we have this for all sets that don't contain A and B, we can leverage it to go back and prove this claim for sets which do contain A and B. So anyway, the basic idea is that for now, we're just going to assume that A lacks those points. And if A lacks those points, then J and L will form an open interval cover of A. Now, it's also straightforward enough to prove that if you intersect an interval, right? I sub n is some open bounded interval, and if you intersect it with any other interval, absolutely any interval, you get another open bounded interval. That's pretty easy to prove, so I leave that as an exercise. Also, if you take the length of I sub n, it's again just, you know, give I sub n some names for its endpoints, and then you can very easily prove that that the length of I is the same thing as the, you know, length of J plus K plus L, right? So again, that's very easy, right? That's a fairly elementary proof, so I'm not going to get bogged down with that right now. So I leave that as an exercise. You know, it mostly just comes down to giving names to all the components and maybe considering some cases or something like that, but it's really not hard. So once we know that the lengths decompose in that way, then if you're summing over all the lengths of the I sub n's, you can split them up, group the part that's like I kind of described it, covering only the interval from A to B, which is to say, you know, you group just the KNs together, and they form, right, the KNs form an open interval cover, so the sum over the lengths by definition, right, like M star is a lower bound on that sum, and so you can kind of, you know, distribute the sum, round that part down, and you get this inequality for that part of it. Likewise, you can group the J's and the L's together, and by the same logic, you know, those two are an overestimate of the set A, and therefore we can do an inequality in this direction with M star of A. Again, because M star, by definition, is a lower bound on those overestimates. As described before, that suffices to show that M star of A union G is greater than or equal to the distributed sum. So next, how do we extend this proof to the cases where the set A does contain the points A and B? Well, I claim, and I will prove in a moment, that adding or deleting points, any set of measure 0, never changes the measure of a set. So, to show you kind of how that would work here, before I state and prove the theorem that's going to let me make these moves, I'll just go ahead and show how the moves go, and that kind of motivates why we would state and prove the theorem which makes this all work. So if A does contain the points A, B, then let's let B be the set minus those, apply the previous result, and we know that this equality holds from the fact that the previous result holds. Now, as I claim, if a set has measure 0, which this is a theorem to be proved, but if a set has measure 0, like this does, right? This has measure 0 because it's countable. Then by putting these points back in, right? If we take B and union it with the set A, little ab, then this measure is exactly the same as the measure of A. And if we do it again over here, then the measure of this is exactly the same as the measure of A union G, which is the same as if you took B union G and union that with the set of little ab. Right? So basically by inserting this measure 0 set, the measure is unchanged. So now we have to prove that this principle that I am using is valid, so we'll go ahead and state and prove a theorem that demonstrates that this is a valid argument. So here's the theorem. If any set has measure 0, then for every other set of real numbers, the measure of the union, A union E together, is always equal to the measure of A. Right? Adding E in does not change the measure of A. The proof is extremely simple, extremely fast, makes for an excellent thing to put on an exam, because it uses all the hits, right? It uses here monotonicity, it uses here subadditivity, and then this is just using the fact that the measure of E was assumed to be 0. And then since, m star of A is less than or equal to this thing which is sandwiched in between, under m star of A, then that must mean that m star of A is equal to m star of the union. So, so that's, I think, a particularly wonderful proof. And there you have it, right? So there you have that putting in any set of measure 0 never changes the measure of the set. And it's a very simple proof if you also wanted to state and prove that if you deleted a set of measure 0, that also does not change the measure of the set. Okay, so with all of that now done, a very, very easy inductive argument proves that all finite unions of open intervals are relatively additive. All you have to do for any finite union, basically, is to take your set A, split off one of the unions, apply relative additivity, my hands are in the wrong place when I'm saying that, but basically, right, split off one of your open sets, apply relative additivity, split off another, apply relative additivity, work it, and eventually this has to terminate. So you can sort of make that rigorous in a simple inductive argument. I'm not going to get into it any more than I already have. So, so then we need to show that it holds for countable unions. And that'll be the end, right? Because once we know that it holds for countable unions, well, every open set can be represented as a countable union of open intervals, as we've seen before. And not just that, by the way, we have seen that we can take these intervals to be disjoint, and that'll be valuable in what we're about to do. So if you take your set G to be equal to this countable union of open intervals, we can chop it off, right? We can end this union at any, right, finite stage M. And this holds by monotonicity, right? Because just more sets in the union means necessarily a bigger set. So this is monotonicity. This is relative additivity coming from finite unions, right? And this is coming from disjointness and the fact that open intervals, finitely many open intervals, are relatively additive here too, right? So if you basically just take the sum over all of these measured, right? This is just, again, using relative additivity on a finite union. And so we get that this set is greater than or equal to that set. If we let M go to infinity, then we know that, that this M star is greater than or equal to the infinite sum. And the reverse inequality, as usual, holds by subadditivity. So with all of that in place, the proof is complete.